Welcome back to G Fun Facts Online. Today we are going to talk about the ground beneath your feet and the roof over your head, but not in the way you might expect. If you look back at the history of human civilization, particularly the last 100 years, our relationship with infrastructure has been incredibly passive. It has been a story of decay. We build a bridge, time passes, the bridge rusts, cracks appear, and then, usually too late, we rush in to repair it. It is a cycle that has drained trillions of dollars from the global economy. In the early 2020s, the infrastructure deficit in the United States alone was estimated at over $2.5 trillion. That is the cost of letting things break. But it is January 2026, and as we stand here today, that script is finally being rewritten. We are witnessing the birth of what engineers and scientists are calling the immune city. Just as your body heals a scratch on your arm without you having to consciously think about it, our cities are beginning to heal themselves. We are moving from dumb, static structures to smart, dynamic systems that can sense injury, diagnose the severity, and initiate a cure. This is not science fiction anymore. Pilot projects in the Netherlands, the UK, and Japan have graduated from university labs to public highways. So today, we are going to do a comprehensive deep dive into the science, the technology, and the economics of the self-repairing city. To understand the solution, we have to understand the problem. Let's start with concrete. It is the second most consumed substance on Earth, right after water. It is the backbone of modern life, but it has a fatal flaw. It cracks under tension. Microcracks are inevitable. They might be invisible to the naked eye, but they allow water, oxygen, and de-icing salts to penetrate the structure. Once that water reaches the steel reinforcement bars, the rebar, inside the concrete, the steel rusts. When steel rusts, it expands, and that expansion shatters the concrete from the inside out. This is why bridges crumble. The first line of defense in this new immune city is biological self-healing concrete. This technology was pioneered by researchers like Professor Henk Jonkers at TU Delft, and by 2026 it has really matured. The concept is fascinating. They treat concrete not as a dead rock, but as a host for dormant life. They mix in specific strains of bacteria, typically bacillus species, which are extremophiles. These bacteria can survive in a dormant spore state, encased in rock, for up to 200 years. They are encapsulated in biodegradable plastic or clay pellets, along with a food source, usually calcium lactate. Here is the mechanism. When a crack forms in the concrete, water enters that crack. That water dissolves the pellet, waking the bacteria up. Suddenly, you have these hungry, active bacteria inside the wall. They consume the calcium lactate, and, as a metabolic byproduct, they excrete limestone, or calcite. They essentially poop rock. Over the last year, in 2025, we saw this technology scaling up significantly. These bacteria act as a biological mortar, filling cracks up to 1 millimeter wide in just a matter of weeks. The result is a structure that effectively scabs over, sealing the pathway against water and salt, and stopping corrosion before it can even start. But the science didn't stop at bacteria. Between 2024 and 2025, researchers at Washington State University and other hubs began expanding into fungi. Fungi function differently. They have hyphae, which are these long branching filaments. These hyphae can grow faster and bridge larger gaps than bacteria, effectively knitting the concrete back together like microscopic rebar. And then there is the work from the University of Colorado Boulder and TU Delft using photosynthetic algae. This is a game changer because the algae doesn't just heal the crack, it sequesters carbon dioxide during the process. It turns the building itself into a carbon sink. Now, biology isn't the only way to solve this. Material scientists have also looked at the human body for a different kind of inspiration, the vascular system. In vascular self-healing, engineers embed a network of hollow tubes or channels within the concrete. These tubes are filled with a liquid healing agent, like sodium silicate or epoxy. When a crack ruptures one of these tubes, the pressure differential causes the healing agent to flow into the crack, where it polymerizes and hardens. The breakthrough we saw in 2025 was the development of multi-cycle vascular systems. Unlike the bacterial capsules, which are one and done, these vascular networks can be refilled from an external tank. Imagine a bridge that can be refilled with healing fluid, allowing it to repair itself repeatedly over a 100-year lifespan. So that covers the buildings and bridges. But what about the roads? While concrete supports our weight, asphalt supports our movement. And asphalt is notoriously fragile. The problem here is UV radiation. The sun oxidizes the bitumen, that's the black glue holding the stones together, making it brittle. Then, the traffic load causes fatigue, and suddenly, you have a pothole. By 2025, the UK was facing a pothole crisis that cost its economy nearly £150 million annually. This crisis turned the UK into a testing ground for AI-designed asphalt. In early 2025, a massive collaboration between Swansea University, King's College London, and researchers in Chile unveiled a new generation of asphalt designed by artificial intelligence. The AI modeled the molecular behavior of bitumen to create a mix that includes tiny porous capsules filled with a rejuvenator. This rejuvenator is often derived from biomass waste, like sunflower oil. It works on a simple trigger mechanism. When the asphalt cracks, the capsules break. They release the oil, which softens the oxidized bitumen, restoring its flexibility and stickiness. It is essentially moisturizing the road from the inside. However, the most visually spectacular method for fixing roads involves magnetism. It's called induction heating. This approach involves mixing steel wool fibers into the asphalt mix. Now, steel is conductive, but asphalt is not. When a road begins to show microcracks, a maintenance vehicle equipped with a large induction coil drives over it. The coil emits an electromagnetic field that heats those steel wool fibers buried in the road. This heat radiates into the surrounding bitumen. At around 85 degrees Celsius, the bitumen transitions from a solid to a viscous liquid. It flows into the microcracks, effectively resetting the pavement. Studies from the Netherlands have shown that this heat treatment can double the lifespan of a road, taking it from 10 years to over 20. Now, all of these materials, the bacteria, the algae, the steel wool, are impressive, but they are technically dumb. A bacterium doesn't know why a crack formed. It just reacts to water. To create a truly resilient immune city, we need a brain. This is where the Internet of Things, or IoT, and digital twins come into the equation. In the smart infrastructure projects of 2026, the concrete itself is a sensor. By adding conductive fillers like carbon nanotubes or graphene to the mix, the entire structure becomes piezo-resistive. This means that when the concrete is compressed or stretched, its electrical resistance changes. A bridge deck made of self-sensing concrete acts like a giant scale. It can weigh every truck that passes in real time. It can detect seismic activity invisible to standard sensors. And most importantly, it can detect damage. A crack breaks the electrical circuit, pinpointing the exact location of the failure. This leads us to the holy grail of infrastructure engineering, the active closed-loop healing system. We have actually seen this in pilot forms late last year. Let me paint a picture of how this works on a bridge in 2026. First, an embedded fiber optic sensor detects a strain anomaly in a specific sector of the bridge deck during a winter storm. That data is transmitted instantly via 5G to the bridge's digital twin, a virtual replica running in the cloud. The AI analyzes the pattern and confirms that a stress fracture is forming due to thermal contraction. Then, the digital twin takes action. It sends a command back to the physical bridge to activate an embedded resistive heating layer in that sector. The heat activates shape memory polymers or melts bituminous capsules embedded in the material. The crack closes. Finally, the sensor reports that strain levels have returned to normal, and the digital twin logs the repair. No human crew was dispatched. No lanes were closed. No traffic jam occurred. The bridge simply healed itself. So where is this actually happening? This isn't just theory anymore. Following the 2025 trials, parts of the UK's strategic road network have begun incorporating that Swansea-developed biomass asphalt. The goal is twofold: eliminate potholes and reduce carbon. Traditional asphalt relies heavily on fossil fuels, but this new green asphalt uses waste oils and lasts twice as long, slashing the carbon footprint of road maintenance by up to 40%. Then we have the Living Wall at TU Delft in the Netherlands. The Netherlands has always been the Silicon Valley of water and concrete. Their green village serves as a regulatory-free zone for testing. In 2025, the Living Wall project demonstrated a quay wall that not only heals its own mortar cracks using bacteria, but is designed to be bioreceptive, encouraging the growth of specific mosses and plants to insulate the building and clean the urban air. And we can't ignore the IT sector. While not concrete, the concept of self-healing has matured fastest in data centers. Companies like Dell and Netflix have perfected the artificial intelligence of things. In 2026, data centers are being built with smart skins, building envelopes that regulate their own temperature and heal minor breaches to ensure the pristine environment required for the AI processors inside. Now, you might be asking, if this is so great, why isn't every road self-healing yet? The answer, historically, was cost. Self-healing concrete can cost 20 to 30% more upfront than standard concrete. However, the economic model of 2026 has shifted. We have moved from focusing on CapEx, capital expenditure, to TOTEX, total expenditure over the life cycle. Let's look at the math. A traditional road might cost $1 million per kilometer, but it requires patching every 2 years and major resurfacing every 10. The total 50-year cost ends up being around $5 million per kilometer. A self-healing road might cost $1.3 million upfront, but if it heals itself using bacteria or induction for 20 years and only needs resurfacing at year 25, the total 50-year cost drops to around $3.5 million. The savings are massive, And the savings are not just in materials, they are in uptime. The cost of closing a major highway for repairs is measured in millions of dollars of lost productivity per day. Self-healing infrastructure buys time and reliability. Furthermore, the carbon credit market is driving adoption. The cement industry is responsible for roughly 8% of global CO2 emissions. Any technology that extends the life of a concrete structure by 50% is effectively a massive carbon reduction tool. In 2026, governments are offering tax incentives for high durability materials, making the expensive bacteria-infused concrete cheaper on paper than the cheap stuff. Despite the optimism, there are still challenges. Standardization is a big one. There is no global standard for how healed a crack must be. Construction codes are slow to change. There is also the question of longevity. Bacteria can sleep for 200 years, but will the biodegradable capsules survive that long? We need to ensure the healing agent is still viable 50 years after the pour. And then there is cybersecurity. A bridge that can be heated remotely via IoT is a bridge that can be hacked. Ensuring the digital twin is secure is just as important as ensuring the physical rebar is strong. Looking forward to 2030, we expect passive self-healing using bacteria and capsules to become standard in critical infrastructure like tunnels, dams, and seawalls. Active systems like induction and vascular networks will likely dominate high-value assets like airport runways and smart highways. We are witnessing the end of the dead city. The city of the future is a living, breathing, sensing, and healing superorganism. It protects us, and finally, it has learned to protect itself. Thanks for listening to G Fun Facts Online. I hope you never look at a pothole the same way again.